Question? No. All right, so acceleration, remember that acceleration is related to change in velocity. So if acceleration is not constant, the change in velocity is not constant for some unit of time, which ultimately means velocity is not constant in that case. Then what is this? This deals with change in velocity. What does this one deal with?
Change in speed.
Yeah. More specifically, speed.
Because it doesn't have the vector sign over it?
Say it again?
Because it doesn't have the vector sign over it?
Absolutely. So if your speed is constant, in this case, because scalar acceleration is constant. So imagine you're in a car going 50 miles an hour. Velocity is not constant, but acceleration, but your speed is constant. How could that be?
Direction.
Yes. And ultimately, that's the key there.
So your direction is changing, but your speed isn't.
Correct. Now, we'll get to this a little bit later, but if you're going in a circle at a constant speed, because in chapter 3, the change in velocity is in Hewitt, the change in velocity is dealing because there's a change in speed. When you get to chapter 8, we now start dealing with the change in direction also. And it turns out that if I'm traveling in a circle, let's say I'm going counterclockwise, the direction of my acceleration is towards the middle. This is known as centripetal acceleration. And so that acceleration is always pointing towards the center. So as you travel in a circle at a constant speed, your acceleration, the vector acceleration changes because the direction changes.
Would that happen with a spinning object? Would that happen with a spinning object also?
Yes. Anything that's moving, anything that's going in a curve. It's just that if it's a circle, then specifically there's a middle that it always points towards. If it's, a changing curve, then officially the center changes also. Yes. Tana, you're the one who asked it. Was your question answered?
Yes.
Okay. Other questions? I always feel like that one that you asked about is probably one of the harder conceptually. But, good question.
I think you told me to remind me about that last question I had on that other lab, on why that lab.
Oh, yes, that was the other one. On the lab I handed back, there's that last question of what does this lab prove? And this is one that I was not gonna help you with, just because I wanted to see what your answers were. I gave one person some points for it, everyone else got no points for it. It's sort of like a bonus question. And if there's a question that I ask that everyone misses, then it's probably a bad question. This one in particular, I like the question, but if there's a question that everyone misses, I tend to sort of throw it out. So it really does come. It hasn't hurt you if you didn't get it right. It just didn't help you. So if I drop a ball from 2 meters up and it bounces up to 1 meter 5 times in a row, is it going to bounce up to 1 meter on the 6th time?
Yes.
We got a yes and a maybe.
I don't think so, because 5 times in a row, we did.
All right, so when doing any science, ultimately the answer to this comes down to my personal philosophy of science. I think science in general, it's not just me. But in physics especially, we have to assume that if I drop something from 2 meters and it bounces up 5 times in a row, it is possible that it was just some freak coincidence that it happened to bounce up to about the same thing each time. Just because it happens 5 times does not necessarily mean it's gonna happen the 6th time. Or if there's a huge spectrum of bounces it's gonna do, you might, for some reason, might be getting them down here when the average actually would have been here. If we did 1,000 trials, we might get something completely off that. So we never actually prove anything in science. What we do is we come up with a hypothesis. We make hopefully an educated guess about the underlying reason why things happen. And then we perform an experiment which will support that or not support that. And that's ultimately what we do, is we support theories or we don't support theories. We never prove anything. So, if I'm recalling correctly, the one person who got some points, there was an acknowledgement of, I think the acknowledgement of this is very limited experiment. Really is no way of knowing what would happen if we kept going. Now my memory could be off, but I think that was the essence of it. So that the last one was basically, we don't prove anything. So therefore, when we were doing formal lab reports, and you're not doing a formal lab report, so if you in a moment of panic and you missed reading that earlier, relax. But the biggest penalty I think I gave is that if you use the word prove or proven, or some variation of that, was the biggest penalty. Because you should never say we proved anything. We're supporting, we come up with an idea. We think that if I jump off the table, I'm gonna land on the floor. Now, we can experiment with that and we keep going, well, it happens every time we do it. I'm feeling like that's a pretty good idea of what's gonna happen there. But especially when you get into quantum physics, there's always a non-zero probability that something really bizarre is gonna happen. There's a non-zero probability I'm gonna suddenly, poof, seemingly disappear and end up on the floor below. I'm not putting money on that, but it's a non-zero probability. Quantum physics, just when you think you might know what's going on, it's time to mess you up. Other questions? All right. Let's talk about chapter 6. Just for the sake of keeping track, let's